November 2016. Fukuoka, Japan. Without warning, a 30-meter wide, 15-meter deep crater swallowed 5 lanes of road, just meters from a busy train station. Gas, electricity, water, and communications, all cut at once. Over 100,000 residents lost access to daily infrastructure within minutes. The road was repaired in just 6 days. Impressive engineering. Yes, but the repair bill ran into hundreds of millions of yen. And just weeks later, the ground sank again. Speed of repair does not mean safety of the underground. January 28, 2025. Yashio City, Saitama. A 40-meter sinkhole opened in seconds. A truck vanished into the earth. The 74-year-old driver was never rescued alive. His body was not recovered for 3 months. The cause? A sewer pipe installed in 1983. Corroded by sulfuric acid for over 4 decades until the pipe wall, once 50 centimeters thick, was worn down to just 10. The cost of this one sinkhole, 3 billion yen, over $20 million US. 1.2 million residents were disrupted for months. The government survey that followed found 72 kilometers of pipes across Japan in critical condition. Today, 7% of Japan's sewer pipes are over 50 years old. In 10 years, 19%. In 20 years, 40%. In the United States alone, sinkholes cost an estimated $300 million every year. But this is only what we can see. The real danger lies in what we cannot. 2018, Surabaya, East Java. A hospital, a place of healing, became a place of crisis when the ground beneath its parking structure gave way. A 30-meter wide, 15-meter deep void opened without warning. No detection, no prediction, no preparation. December 3rd, 2025. Aceh, Indonesia. Drivers watched in panic as the road in front of them disappeared in seconds. A 20-meter sinkhole swallowed the highway whole. In the surrounding disaster, over 807 people lost their lives. 1.2 million were displaced. Economic losses in Sumatra alone, $4.13 billion US. January 2026. West Sumatra. This time, not a road, not a city, a rice field. A farming community's entire livelihood. A hole more than 10 meters wide appeared overnight, growing, deepening, unstoppable. 30,000 square meters and still growing. Depths reaching an estimated 100 meters. Edges collapsing at 1 meter. Every single day. Farms destroyed. Communities threatened. And no technology in place to predict when or where the next collapse will come. From Surabaya to Sumatra. From rice fields to highways. The ground is giving way across Indonesia, and the economic cost is measured not in millions, but in billions. The question is no longer if the next collapse will happen. The question is, where and when?
Every one of these disasters had one thing in common. No one knew the void was there until it was too late. Today, I want to share with you a technology that can change that. A science of seeing the invisible. Developed and refined in Japan, and ready to make a difference here in Indonesia. The subsurface mapping technology simultaneously captures subsurface data with a GPR and surface data with a 360-degree camera. After both data are synchronized with GPS time, a unified database for efficient and high-precision infrastructure management is created. The subsurface mapping technology is composed of the GPR, camera, and GNSS, meaning that it can be installed with the same potential in different platforms such as hand-pushed carts, smaller or larger cars. This flexibility allows rapid deployment across diverse urban environments. Feature 1. 3D ground-penetrating radar system with multi-channel antenna arrays. Many antennas are aligned transversely to capture data in the additional dimension transversal to the antenna's travel direction. This allows for easy visualization of data in 3 dimensions, since the geometry of features can be seen in a horizontal slice. Cavities and buried pipes, which are difficult to differentiate in single-channel data, are easily identified. Feature 2. Mobile Mapping System. The differential of the subsurface mapping technology in GPR survey is the addition of a mobile mapping system, or MMS. The system tracks reference points in the camera imagery to calculate the vehicle's accurate position and trajectory in a method called camera vector. The high-precision camera vector trajectory is then utilized to correct the GPR spatial information data, as well as to create an ortho image of the surveyed road. Feature 3. Unified terrestrial and subterrestrial data. This is what data visualized in the subsurface mapping technology viewer looks like. At the upper left, we have the GPR subsurface data. Next to it, the 360-degree camera imagery. At the bottom left, we can see the ortho image created with the camera imagery. And finally, we also have a localization map. The interesting thing about the viewer is that when checking an exact location in the GPR data shown by these blue cross lines, that same location is also displayed in the camera imagery by this blue arrow and in the ortho image by the blue circle. This ultimately allows for accurate and practical localization of subsurface features as seen from the surface, making it easy to understand where an underground feature is with the use of surface reference points. Feature 4. Exploration Vehicle. With the subsurface mapping technology, we can utilize subsurface data as a fixed reference to spatially localize surface imagery previous to the disaster event. It is then possible to superpose the old imagery with the new data to know where buildings, roads, or land borders used to be, providing critical information for disaster response and urban reconstruction. Now, let us turn our attention to the practical application of this technology. Recently, we successfully deployed our system in Thailand, a region facing rapid urban development and complex challenges in underground infrastructure. We needed a solution that was non-destructive, highly accurate, and efficient. As you can see here, the system was mounted on local utility vehicles, scanning kilometers of urban roads seamlessly without causing any major traffic disruptions. Because the subsurface mapping technology easily adapts to different types of vehicles, we were able to quickly mobilize our team and begin large-scale data collection immediately. Between 2025 and 2026, we conducted an extensive survey covering approximately 800 kilometers of roads. During this period, our system successfully detected around 600 underground cavities, 600 potential sinkholes, identified before a single collapse occurred, 600 disasters prevented. By organizing these detected cavities onto a comprehensive map, we are currently conducting heat map research to visually identify and predict high-risk areas. This moves us from reactive response to proactive prevention, knowing where the next sinkhole might appear before it does. We are proud to share that our findings were recently reported at the NCCE 30 conference. This landmark study represents the first ever trend analysis of large-scale cavity investigations in Thailand. Based on a comprehensive 338-kilometer survey, we successfully identified distinct cavity formation trends across different urbanization zones and road lanes. Furthermore, through advanced physical tests and finite element analysis, we are developing a novel risk assessment framework tailored specifically for Bangkok's concrete pavements, moving beyond traditional asphalt-based standards. Furthermore, we are thrilled to announce the publication of the very first technical standard for underground cavity investigation in Thailand. This groundbreaking document was developed and published based on the successful outcomes of our joint research with Ehime University and King Mongkut's University of Technology Thonburi, or KMUTT. This standard will serve as a vital guideline for standardizing proactive road maintenance and preventing road collapses across the nation. We will continue to work in collaboration with universities in Thailand and Southeast Asia to address the challenge of promoting the GMS3 technology, which is the most effective solution for preventing cave-ins caused by underground cavities.